Okay, everyone, welcome back to week 9 lecture series. Here we are diving even deeper into our survey of statistics. And today we're going to look at section 7.2, where we're talking about frequency and probability distributions, as well as something called random variables. So let's dive right in. So we talked about sort of in passing, the idea of frequency and frequency tables in section 7.1. So here we're just going to discuss it in more detail so that you have a firm grasp. So in order to understand the idea of frequency, let's look at an example. No better way to get our hands wrapped around this idea. So here in this example, we're tossing a coin 5 times consecutively. And at the end of tossing it 5 times, we will have recorded the number of occurrences of heads in those 5 coin tosses. This experiment is conducted 90 times in total. Okay, so down here we have what's called a frequency table. And the frequency table lists all the possibilities, as well as how many times those particular occurrences happened in our series of experiments. So reading this table, we see that out of the 90 times that we flipped the coin 5 times, the number of times that we had no heads, which is to say all tails all 5 times, that happened 3 out of the 90 times. The number of times that we flipped a coin 5 times and got only 1 heads out of the 5 was 14 out of the 90 experiments. The number of times that we got 2 heads was 23. The number of times that we got 3 heads was 27. 4 heads, 17. 5 heads, 6. So a frequency table in its most essential form just consists of what are the possibilities and how many times did those possibilities occur within your series of experiments. Okay, so frequency tables are great, but it's hard to necessarily compare the results that we got for our frequency directly, because these are just counts, and sometimes it can be hard to see how big of a difference there are in the counts. I mean, we see a 3 and we see a 27. We know that those 2 numbers are seemingly have a big difference, but we don't know what fraction of a difference they have in this particular context. So in order to compare these results more clearly, we determine what's called the relative frequency. So in section 7.1, we saw that there was frequency and they showed percentages. Relative frequency is related to percentages and can really be translated directly into a percentage. But when we're talking about relative frequency, we're really talking about a decimal form of a percentage. So let's see how we would calculate it in this case. So for the first row, we're looking at 0 heads that happened 3 times. Now, what's important to know is what is the grand total of experiments. And we know that that should tally to 90. Okay. So this is 3 out of 90. And so if I calculate that, 3 out of 90 gives me 0.033. Okay, so that would be considered my relative frequency for this first slot. Now we could do it for the next 1 heads. There are 14 occurrences, so that's 14 out of 90. And so that gives us 0.156, I'll say. I'll round to 3 decimals here. And so this is how we develop our relative frequency. We take the frequency and then divide by the total number, which we can get simply by adding up all these numbers. If we took 3 plus 14 plus 23 plus 27 plus 17 plus 6, that would add up to 90. Then all we have to do is to get our relative frequencies is take each individual number and divide it by its total. So if I go through this for all of the occurrences, then this gives us all of our relative frequencies. Okay, so as I said, these are just like percentages, really. So I can see this first relative frequency as 3.3% of the observations had no heads. Here we have 15.6% had 14 heads, had 1 heads, 25.6% had 2 heads, 30% had 3 heads, 18.9% had 4 heads, and 6.7% had 5 heads. So that's how relative frequency works. And you can see that it's easier to compare these results. Now we know that this is 30% and this is 3%. So this is a whole order of magnitude different. This is 10 times larger than the occurrences of heads. So 10 times more occurrences of 3 heads out of 5 flips than 0 heads. Okay. Now, it's often useful to represent this information graphically. And as we discussed in section 7.1, when we're dealing with quantitative data, we use a histogram to represent the data graphically. And with histograms, you have bars that are all touching. And here on the vertical axis, we could have either the frequency or the relative frequency, but it's often best to use the relative frequency for the same reason as noted before, that the relative frequency is easier to compare, okay? So graphically, we can show that the relative frequency looks like the following, okay? This is the shape of the distribution, okay? Now, if we're using the relative frequency on our vertical axis, then there's something useful that comes out of this representation, which is that if I want to calculate a probability of a certain event within the experiment, I can simply figure out what the subset of that event is to the sample space, and then add up the areas of the rectangles that correspond to that subset. So for instance, if I wanted to calculate the probability that out of 5 flips, there'll be less than 3 heads, how would I calculate that? Well, that would be equivalent to either getting 0 heads, getting 1 heads, or getting 2 heads. So that's all the possibilities of having less than 3. Now, in order to get the result here, we can actually use the diagram or the relative frequencies. So P of 0 should be equal to the relative frequency of 0. So that is 0.033. P of 1 is the relative frequency. So that's 0.1. So that's 0.156. I'm sorry, 0.0156. And, oh, sorry, no, 0.156, sorry. 0.156, and then the probability of getting 2 heads corresponds to this relative frequency, which is 0.256. Now, these numbers actually are equivalent to the areas of these rectangles. So if I calculated the actual area of this rectangle here, here, and here, in each case, I would get the relative frequency back. So the area for this rectangle is 0.033. The area for this rectangle is 0.156. and the area for this rectangle is 0.256. So we can use the areas to help us calculate probabilities. So once we have the areas, which correspond directly to the relative frequencies, then we can just add them all up. 0.033 plus 0.156 plus 0.256. And that gives us 0.445. So the probability of getting less than 3 heads out of 5 flips, according to our experiment, is 0.445, or 44.5%. Okay. So we're now going to make this topic a little bit more mathy. So instead of just dealing with empirical evidence, that is evidence or data that is generated through experiments, now we're going to do sort of thought experiments or use mathematical reasoning to figure out what the results would most likely be for a given experiment. So in this case, instead of dealing with data, we're going to first define what we call a random variable, and the random variable will generate the data. Okay, so what is a random variable? So we typically use a capital letter, in this case a capital X, to denote a random variable. And a random variable is a lot like a regular old variable in terms of the fact that it has an input and an output. The way that it differs from a regular variable is that its output is randomized. So its output is determined by chance. We don't know exactly what the output would be for a certain input. So we call this thing a random variable. So let's look at an example. If I define my random variable X to be equal to the number of heads that are observed out of 5 coin flips, then I can mathematically determine the probabilities of certain outcomes. So X counts the number of heads. In this case, I make a probability table or a probability distribution table to represent all of the information. So here are all the possibilities for what the possible outputs of X. So X can be 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, or 5 heads. And then here we have the associated probabilities of getting those particular outcomes. So these are calculated using mathematical reasoning, and we won't go into the finer details of how this is calculated. Just take it on faith that these are the correct numbers. And so what this is telling me is that the probability of getting no heads out of 5 flips is 1 out of 32, versus the probability of getting 3 heads out of 5 flips is 10 out of 32. Okay, so remember what this is. This lists all the possibilities and their corresponding probabilities. So we learned about this in a previous section, I think back in chapter 5, when we were learning about probability. This is called a probability distribution. And remember that in order for this to be a probability distribution, it has to satisfy 2 conditions. One is that all the probabilities listed must be between 0 and 1, which we can clearly see these are all positive and they're all less than 1. The second condition is that if we add up all the probabilities, then the sum should equal 1. So I'm claiming that this is a probability distribution. So in order to prove it, I have to make sure it satisfies those conditions. So 1 is easy, right? All the probs are definitely between 0 and 1. For the second condition, we need to do some math. So here we're going to add up all the probabilities. So the sum of the probs is equal to 1 out of 32 plus 5 out of 32 plus 10 out of 32 plus 10 out of 32 plus 5 out of 32 plus 1 out of 32. And if we add all of those up, we add up the numerators and we get 32 out of 32, which is indeed 1. So this qualifies as a probability distribution. Now, probability distributions are really just like relative frequency tables. The only real significant difference is that probability distributions are determined through mathematical reasoning, whereas frequency distributions are determined by empirical evidence, by data that's generated through experiments. Okay. So a random variable essentially is a mathematical way of modeling the experiments that we do in real life. So the X is kind of standing in place of the experiment, and we're when we're calculating the probabilities, we're kind of assuming that everything works out perfectly. So let's look at another example of a random variable. So in this case, I'm going to define my random variable to be the sum of the upper faces when rolling a pair of dice, right? So both a die, an individual die has 6 sides. Each side with a number between 1 and